Hi, this is Professor Cummings, and I want to do another video here to discuss implicit differentiation and how it relates to related rate problems. So this will be, one problem that we wanted to go over. It's a good one to go through because it really shows making a mathematical model to a actual scenario. We looked at heating and cooling problems and growth and decay and mixing problems. Now this one is one where you don't have such a straightforward problem. You've got something that actually has to be evaluated the way you will most engineering problems. So why do we use this? So as you see here is we got a tank here, and this is kind of a classic related rates problem. A tank with a given height in the storage tank and a flow rate going in and a flow rate going out. Now it's a different type of problem. I want you to see how it's working here, but let's go through a little bit more while we discuss it. All right. Okay. What you have in a related rates problem is multiple variables that are changing and with respect to some sort of independent variable. All right. So there's a variable there that just isn't going to change. And in order to find the differential equation, you have to use implicit differentiation to get there. From there, you can actually create a model to predict the change that you're trying to keep track of, you're trying to understand. All right, so in this particular case, we've got a water being pumped into the tank at 5 cubic feet per minute. So that's already a derivative, change in volume with respect to time. That's what a flow rate ultimately is. And we know that there's a volume to the tank, so pi times the radius squared times the height. So what we can do is we understand that there is a phenomenon already taking place. The water is being pumped to the tank. We go where there's a volume equation to the tank, and we know that there's a derivative, at least one derivative that we're going to be working with. So if we wanted to understand how long it would take for that tank to, or as how long the height would take, or come up with a model for that height change in the tank, we'd need to come up with some sort of a way to make this differential equation, or make this into a differential equation. And we do have a flow rate that we can work with. So what do we know? We know that it's a cylindrical tank, obviously, and we know that the radius is going to be a constant. That's not going to change. The only thing that's going to change is going to be the height, which means that the volume is indeed changing. All right, so we've got sort of a rate there. So we could take this equation, and through differential equation, or take an implicit differentiation, we can actually come up with a differential equation that puts this in respect to time. Right, so from there we can actually come up, if we went further, create a mathematical model to actually show how long or what that new height is going to be at any given time, so long as this flow rate is in place. Now let's look at implicit differentiation, but before we do that, let's look at explicit differentiation, trying to show the difference between the two. In most of the problems we've had y, stated explicitly in a function of x. Or some variable explicitly as a function of another. And this particular would be equation be an example, y is equal to x squared. And if we wanted to differentiate this equation, it's pretty straightforward. Dy over dx is equal to 2x. It's just the power rule of taking a derivative, right? Same with this equation, y is equal to the sine of 3x. Again, that's a pretty simple differential equation or way to take a derivative. Dy over dx is equal to the cosine of 3x, or 3 times the cosine of 3x. All right, so that's just taking a derivative, and that's actually the chain rule, right? So that's just the power rule, the other was the chain rule. So when you take implicit differentiation, y is stated implicitly in terms of x. It's no longer an explicit relationship. So the method of taking the derivative, if the problem, is not separable. So the way you're going to go about doing this is first you want to differentiate everything term by term. Take the derivative of every variable with respect to the independent variable. Second, you're going to collect the like terms. And by that, I mean all of the differentials, dy over dx, on one side of the equation, in terms of the other side. And then you want to solve for dy over dx. So you want to factor out dy over dx and then solve for dy over dx. So it's a pretty straightforward process. And let me give you an example. Again, that's just the power rule up at the top there. So let's look at this example of x squared plus y squared is equal to 4. Pretty straightforward example. This is a really good, I always like to use this as just a very simple implicit differentiation problem. So we're going to differentiate each term independently. As we go through the problem, take the derivative of each one. We're going to isolate and then, solve everything for dy over dx. So if we take the derivative of each term, you've got x squared, it's just 2x dx over dx, plus y squared becomes 2y dy over dx, and the derivative of 4, a constant, just goes to 0. Right now, there's a reason for that, how it looks right now, and I'll explain that in a second. But what we can do is we can factor out, since this dy over dx is just 1, we can subtract 2x from both sides. So we got 2y over dy over dx is equal to a negative 2x. Then we divide both sides by 2y, and then we reduce. That just becomes x over y. So now we've got it solved in terms of dy over dx. So dy over dx equal to negative x over y. The 2's factor out. Now, about this weird dx, or dx over dx, there's a reason for that. Again, everything was done with respect to x, so the derivative of y requires that notation. When you do that for y, it becomes dy over dx. Same goes with the x. That's just an implied one. Now, you don't have to do this particular step. I just did it in this example just to show it, before you can see where this thing came from. So we can see that we're doing everything based on dy over dx, or with respect to dx. So that's the reason it's there. So it's just there just for this example. Otherwise, when we do this problem, we wouldn't even put that in there. So here we have our 3 steps for implicit differentiation. Differentiate with respect to x, collect like terms, and then solve for dy over dx. So we got another problem here. X squared plus y squared minus 2x plus 3y is equal to 8. So again, differentiate everything with respect to x. So you can see what that's going to be. Taking each one of these derivatives, you end up with 2x plus 2y dy over dx minus, this would just be 2. That derivative would come to 2. And then 3y, the derivative of that would just become 3 dy over dx is equal to 8. So we did step 1, differentiate with respect to x. Okay, now we're collecting like terms. In other words, everything that is being multiplied by a derivative dy dx is going to be on one side of the equation. So that means we are adding negative 2 to both sides, or adding 2 to both sides, and subtracting 2x from both sides. So we have been left with 2y dy over dx plus 3 dy over dx is equal to 2 minus 2x. So all we did was, again, just added 2 to both sides, subtracted 2x from both sides. So again, this is what I mean by collecting like terms. Then the next step, factor out dy over dx. So we just factor dy over dx off of both of these. We end up with the quantity of 2y plus 3 is equal to 2 minus 2x. Now we're going to solve for dy over dx, which is just going to divide by this portion here, 2y plus 3. We end up with this as our, the solution to the problem. So it's really straightforward. Again, keep in mind all the rules still apply, of differentiation. So when you take the derivative, you can still apply the chain rule, you still apply the product rule, you still have the quotient rule, all in effect. So the only thing is happening is now you just don't have y explicitly in terms of x. So you're gonna have to use the chain rule and go through everything term by term, taking each one of those derivatives. So we get the second example. X squared plus xy plus y squared is equal to 10. Again, we're going to follow this same set of rules. So you got x squared, its derivative, x times y. You're going to take the derivative, and then y squared's derivative, and then 10's derivatives. So let's see, what would that come out to? That would come out to 2x. Now you got x times y. So you're going to look at the product rule. That's the product rule. So x times dy over dx plus y times dx over dx. Then y squared is 2y, dy over dx, 10 goes to 0. You can see that that's the product rule in there. And then the next step, collect like terms. So again, the only ones with the derivative tied to them, you subtract 2x from both sides, and you can subtract y from both sides. This is just an implied 1, so y comes over to this side. Subtract both of those, so you're left with x dy over dx, and then you've got 2y dy over dx. So you're going to factor that out, and now you've got this term here as x plus 2y, right? And you can solve this in, completely for dy over dx. And this is a solution. So if you're going to trip up, you go back and review the product rule. And you can see, and keep in mind, these are just the derivative of x, and this is the derivative of y. So the term times the derivative plus the second term times the second derivative, or the other derivative. So that's implicit differentiation. Now let's see this used in a related rates problem, which was the whole point of this video. So here you have a problem. Let's go ahead and read through this. All right, so when a rocket reaches an altitude of 40 meters, it begins to travel along a parabolic path of, expressed in this term, y minus 40, the quantity squared, is equal to 160x. Now let's pause here. So we got this grid, the y direction, the x direction, and as this rocket took off, it reached 40 meters, and then it started into a parabola. And this is the function, the term that describes, or the function that describes this parabola. All right. So where the coordinates are measured in meters. So this y is in meters, the x is also in meters. So that's just the displacement. If the component of the velocity in the vertical direction is constant, the velocity going in the y direction only, the y component is 180 degrees meters per second, determine the magnitudes of the rocket's velocity and acceleration when it reaches 80 meters. So let's think about what this is saying here. All right, so if we know that, then they talk about the component in the y direction. It's going to be constant at 180 meters per second. Now, that means there's a x component that's traveling at a distance that we don't know yet, at a velocity that we don't know yet. So there's an overall magnitude to that velocity. When you think about if you broke the velocity up into x and y components, there's the velocity in the y, which is constant, the velocity in the x, which is unknown, and then there's an overall magnitude between the x and y that you can solve through Pythagorean theorem. So that is what they're saying in that the next portion. This second sentence. So again, the magnitude of the rocket's velocity and the acceleration. So that's what we're trying to find. The overall velocity and the overall acceleration when it reaches an altitude of 80. So we're really looking at about right here. If we try to keep this in scale. So we want to know right here what this is going. So this is a related rate problem, and it's actually a little more complicated than most of your related rates problem that we'll see. But this is a related rate problem nonetheless. The reason I want this is because you will see this when you get into kinematics and dynamics. And I have a whole playlist of these problems for that class. But I like this problem because it is a related rates problem, and it's one that I think is a little more plausible to what you're going to be seeing. So let's break this down a little bit. Remember, this was when we first moved into this part of the class. How do you develop a model? Well, there's a few things to keep in mind. You're going to identify all the variables that are involved. You want to see what's being affected, what's being changed. You also want to identify what's being independent. So these are all the things we're going to start looking at. We want to understand the relationship between the variables, and we want to make reasonable assumptions. What influences are there on the system? We don't really have to worry about that with this problem, but we do these first two steps. We want to understand that relationship, or the relationship between the variables, and we also want to be able to identify what's being affected and what's being changed, and what's totally independent of everything else. So let's go back and look at this problem again. All right, so there's the statement. So what's going on here? So we've been given this as the function for the path. We also know the vertical velocity. And I have the acceleration going in the y as 0. The velocity is constant. There's no acceleration. That's just a rule of physics. We want to find the magnitude of velocity and acceleration when it is at a magnitude, or excuse me, at a height of 80 meters, So as this thing reaches a height of 80 meters, we want to know how this has changed. So, how are we going to do that? We've got a function for displacement, but we're being asked to find something with regard to velocity and acceleration. How do we make that leap? Well, there's a way to do it, and it goes to understanding what's being changed, what's independent, as well as the relationship between everything. So we know that the x is the horizontal displacement. We also know that y is the vertical displacement. And we also have a path that describes it as a function, which was given. So we also know that the vertical velocity is constant. So if you've got a constant velocity, it means your acceleration is 0. So the relationship between the variables. So here's something that you need to keep in mind. Velocity is a derivative of displacement, with respect to time. So time is independent. So we read the velocity, the derivative of displacement with respect to time dt. We also know that the acceleration is the derivative of the velocity with respect to time. Another thing to keep in mind, the time is independent. So acceleration is the derivative of velocity with respect to time. So knowing these two, we know that we can take this function, which is really a function about displacement, and we can start taking derivatives and understand a function for velocity and a function for acceleration. We also have this, this is a constant for in the vertical direction for velocity as well as for acceleration. So that's going to come into, a very important thing for us as well, knowing that those are constants. So let's go ahead and look at this problem a little bit more. So we got to find two velocity vectors, right? So that was one thing we know we're going to do. We got a path velocity, and we've got so we need to find the velocities in order to find that magnitude. So this is the first function we've got. So we're taking derivative of both sides. Again, everything's going to be done with respect to t, the independent variable. So here we have 2 times y minus 40 dy over dx. So again, we're going to still apply a lot of our rules for derivatives. And the derivative of 160 is going to be dx over dt. Notice everything's done with respect to dt in this example. So it's no dx dx's, no dy dy's. So since we know that this dy over dx, this derivative, is a velocity in the y direction, we just substitute the velocity for y for dy over dt and velocity for the horizontal direction, dx over dt. So this is just a substitution. Velocity in the x direction, velocity in the y direction. Now we're solving this in terms of dy over dt, or vy is 180 meters per second. Again, that one was given. So y equals 80. So that's what they gave it to us for. Y is equal to 80. Again, remember there's y. So we got 2 within this function, this derivative, 2 times 80 minus 40. This is times 180. Velocity of y is 180. That's a constant. Is equal to 160 times v sub x. That's the only thing that we don't know in this equation. That's the only unknown. So at 80 meters in height, the velocity in the x direction, the x component is going to be 90 meters per second. So again, what did we do here? We did some implicit differentiation. We substituted this, knowing those relationships, that this is the definition of the velocity in the x, this the definition of the velocity in the y. We knew that the velocity in the y was a constant, so we could substitute it back into the equation. And they gave us a height of 80 meters that we were able to substitute in, and that let us solve for x. All right. So then our next thing we needed to do was find the acceleration vectors. So again, remember, acceleration is a derivative of velocity. So we take the derivative of both sides. Again, this is our equation, of our derivative. If we taken this first derivative, and now this is the first derivative of our original function. So this is the velocity. So now we got this equation again, and now we have to take the derivative of it. Again, implicit differentiation. See, now you're starting to get into the chain rule more. So 2 times the velocity times the velocity, or times the velocity plus 2 times velocity minus 40 times the acceleration is equal to 160 times the acceleration in the x direction. Again, just taking the derivative of a derivative. So velocity turns into acceleration. And again, this is the chain rule that we just witnessed here. And the product rule also took place, because you're multiplying this times this. Again. So all we did was went through and did some basic arithmetic. 2 times velocity in the y squared. And this is, plus 2 times y minus 40 times the acceleration. So that's just a little bit of simplification. Now we just do some substitution, because we already know what this is. The acceleration in the y is 0. We don't know the acceleration in the x. That's what we're trying to find. And we also know that the velocity that we're concerned with in the y is 180 degrees. Right? So we got a velocity is 180 degrees. That still was a given. We also know the acceleration of the y was 0. It was so this constant and this 0. So again, and we also know that at 80 meters, what we're dealing with here. So that gives us an equation for the acceleration. Or excuse me, this would actually go to 0. So what we end up with is 2 times 180 squared divided by 160. And divide that by 160, solving for ax. That the x component is 405. So we have a x component for the velocity, x component for the acceleration. And the y component for velocity was given, and the y component for the acceleration was also given. All right, so now we can find the magnitude. Again, I told you that was Pythagorean theorem. So now to find the magnitudes of the velocity and the acceleration. So the magnitude is going to be, since we're talking about basically the components, x and y components, we have the x and the y, the quantity, squared, taking the square root of that. And we have this constant velocity in the y less than 90 when you get to 80 meters. Comes out at 201.2 meters per second. So that's the magnitude, the direct velocity that would be on a speedometer or something tracking the velocity of that rocket. And the acceleration's solved the same way. Since there's no acceleration in the y, we end up with 405 meters per second squared. So again, this is Professor Cummings. That was showing you implicit differentiation. So reviewing that, as well as showing you a related rates problem. All right. Thanks for watching.